In this video, we are going to discuss an interesting blog from our Mosaic AI research team. And actually, is all the different tools and optimizations they've built in order to train DBRX, which is excellent because all of you out there are asking which exactly tools were used to train this model, completely pre-trained. So most of them are open source, so we're going to have a look at them. And as you can imagine, in order to train a big model like DBRX, there are a lot of different components that they have to work together, apart from the infrastructure on the modeling side itself. So there's a lot of different things that compile into a stack that they have to work together. You can see them here. So the stack supports multiple GPU cloud providers, right? So in any cloud provider you are based, AWS, Azure, you can use this stack. It is configured with the latest GPU drivers. And also it has a lot of core functionality around the neural networks and how to train those, like PyTorch expansions, MegaBlock library, Composer. A lot of the optimizations they did, they released it into a Composer library. And then the streaming library, which is how you push the data into the training of the model. Now, apart from all of these, they have created a lot of training scripts to fine-tune, pre-train, and evaluate all the different models, all the different experiments and attempts they did. And this is, again, open-sourced in the LLMFoundry. And it has a lot of cool functionality around evaluation of LLMs. So if you're wondering I have no clue how to evaluate what I'm building, then I think you should definitely go and check this out. Here's a nice chart explaining at each step of the process, which are the libraries and the tools they used. But let's go and see a little bit more in detail the main things they expanded on.
So just to clarify, So that's what you need to use in case you want to train a model from scratch, right?
Some of them are completely pre-training. Some functionality can be used also for fine-tuning models as well.
Interesting. Okay.
So as you can imagine, if we're talking about pre-training large language models, these are very big models that you have to learn how to distribute the model into different GPUs. If your model doesn't fit in one GPU, as the case DBRX, you have to find different solutions of scheduling and training this model, right? So
because you need to replicate it.
Bravo, yes. So what we used to do before is actually take the model and replicate it into each GPU. But what would you do if the model cannot fit in the memory of the GPU? You have to find a different way.
It's too big for it.
Bravo. And this way is the FSDP, as we call it, training, which is the fully sharded data parallel. Well, the model and the optimizer are sharded across multiple GPUs, and then they are gathered into one place only for the operations that is 100% needed, as is matrix multiplication. So think of so every time that you have to collect all of this data into one place, then you create this memory spike, and every time you have to do that, this slows down the process a lot.
Yeah.
And that is why they did even a step further, where they created or they use this hybrid sharded data parallel training, which what it does is it shards the model and the optimizer across a fixed number of replica points. And then from that point, they cloned or they copied this model and the optimizer to the other places that the model has to be available.
So just making sure I understand, so it doesn't fit in one GPU. So they use this fully sharded data parallel training.
Yes.
Where they can, just shard that across multiple GPUs, but then it's slow. So basically they have to use this other thing.
Yes. It's slower. It's better than the distributed data parallel, but still slow. So it went a step further. Yes.
Okay.
Of course, in order to do that, they used the D-tensor of PyTorch. So this is an open PyTorch functionality. And apart from that, in the architecture of the model, the mixture of experts, they also tried to do some parallelism on these experts we're trying to train.
Okay.
And they use the MegaBlocks library that allows them to parallelize this part of the job or parallelize the training of the experts. Now, all of this functionality, they composed it into the Composer library, as long as with some other sequence length parallelism optimizations, like to have a lot of bigger prompts or bigger sequence length into the training dataset.
So here, when you say we integrate all these technologies in Composer, that means now I can leverage all of that through Composer?
Bravo, yes. So Composer, again, if we check out, it's a different GitHub repo that has a lot of different examples and a lot of functionality with what we discussed today.
Okay, yeah.
Now, since we have the setup ready for, we have the best setup to parallelize as much as we can in terms of the model architecture, the next thing is how do we push the data into the model in a nice and efficient way? And if you have all of these different GPUs, it's not easy to just go and stream them from different places, right? So that's why they created this streaming library, which is push into the model as quickly as possible the data from different cloud locations, right? So depending the data are in a cloud location, I guess they have to find a way to very quickly push the data and push it in the right place in the GPU.
Okay.
And also shuffle it in a deterministic way so that they can recreate the experiments in case something goes wrong. Now, all of this, again, is handled through the streaming library. Now, another cool thing that this library does is, apart from shuffling of data, at the end of the pre-training, usually what they are doing is they upsampling the best quality data sets they have to allow the model to learn more from this data set. And this library actually facilitates and helps us this native functionality as well.
Okay.
So you have the model ready in the most parallelism way, parallel way you can get, and then you have a nice library to stream the data in. Now, the next optimization is on the checkpointing. As you know, as we go through the model, we have to checkpoint our model so that we can continue training from a specific checkpoint if something goes wrong. Now, the checkpoints means that every time you write or you load it takes time, it's heavy, and it can be actually big. So they have to also do some optimizations on that, which is again a sharded checkpoint, right? So where each GPU saves or loads part or portion of this sharded checkpoint and the model parameters and of the optimizer. And then they even went straight to the next optimization, which is they write it by one replica and then they read it by one replica and then they redistribute it to the other replicas. Right? So instead of each replica going reading or writing, they allow one replica to read and distribute it to the other replicas.
Makes sense.
This is on the checkpoint while we're training, but if you are considering the training performance itself, so what we're trying to do here is to minimize both the training duration and the cost, given that these models are very big. Imagine for the DBRX, we used 3,072 800 GPUs across 3 months. 3 months this model was running and being trained.
So it can be expensive.
Exactly. So we have to optimize it as much as possible. And the memory usually is the bottleneck here, because what we're trying to do is load in memory all the model parameters, the optimizer, all the gradient, the activation, and how much data we can pass in each iteration, like our batch size, it's really limited by how much memory all the other components have taken. Now, what we want to do is push as big batches as possible, because this pushes the usage of the GPU. We need to use our GPUs as much as possible.
And that we do out of the GPU that we have.
Exactly. And that we do by pushing the batch size. But the batch size cannot be pushed if we have taken all the memory from the model parameters, the optimizer, and etc. Right? So we need to find a way to optimize the loading of the model and the other things so that we can allow bigger batch sizes into the training process. And in order to do that, they used a lot of the PyTorch optimizations for FSDP, as we said, and HSDP, as mentioned above. from the moment you have managed to optimize for the memory, you also need to find a way to profile all of this, or profile how the memory utilization, the CPU and GPU utilization is. And with that, they were using the PyTorch profiler to create all of these, to track all of this log and create benchmarks on how their GPU, CPU, it was, behaving and performing while they were performing the big run mainly. And based on these charts, they were tuning the process. Okay. The next thing you need to do is, since you have all of these GPUs and you have to orchestrate all of these GPUs, as we know, GPUs fail quickly and fail fast. You have to have a way to monitor their and make sure they are in a good state, right? So health checks, as we call it. So for that, they use the NVIDIA's Prometheus metrics exporter, also an open source library that you can check.
Lots of things that they had to manage in order to. This is definitely the next level of.
From very different perspectives, right? So the other thing is the network. So how all of these machines can connect to each other and what happens if there are network errors. So for that, they were using another NVIDIA NCL test and CCL test methodology, which is mainly if you have a node and you have a node, you kick off different tests to your node and then you report back to the health checking API so that you make sure each node is in its state, and if it's not, then you have to change it very quickly so that you have as many nodes as possible to support your training run.
Makes sense.
And the last thing, and maybe the easiest out of all of this, is experiment tracking. So as you go through your different experiments, you have to have a way to log them, keep track of them. And that is, of course, MLflow. So they use the MLflow that all know, when it's open source, to track their experiments and map down all the different parameters they used. And another thing here that is very interesting is that they were making sure that they're evaluating the different checkpoints they were going through with a specific evaluation metric, or they call it the evaluation gauntlet, which is a set of different benchmarks combined into one. So they chose the best for their use case, or the best benchmarks out there. They combined it into one, and then they were starting evaluating on that. Every kind of, every 1 trillion tokens they were evaluating across the 12 trillion tokens that the model was trained on.
Makes sense.
And of course, they logged into the model registry and served through the model serving, as always.
It's really impressive that they managed to do something as sophisticated as building DBRX on the platform and leveraging all those, like tools and approaches. And this is really
so mainly, all the approaches and the tools they use to train that are available for our customers to fine-tune or pre-train their own models. So the same stack will be used if you guys want to train your own model. So it's really, that's why DBRX was used, right? To make sure that we have the platform to support the best, to support building the best pre-trained models out there.
Yeah.